So this is example 6, theorem 2. All right, this is the theorem that we're dealing with, algebraic rules for Boolean functions. So what we just learned is how to take a truth table and turn it into a Boolean function. Sometimes they'll just give you a Boolean function, but what you want to be able to do is manipulate it. And this is exactly the same stuff you did in algebra with decimal numbers, you know, in the 9th grade, 10th grade, whenever. Except we're doing it with Boolean functions. So there's a different set of rules, right? So the theorem is each rule states that two different looking Boolean functions are equal. That is, they look different but have the same table. Keep that table in your mind because the table makes it easy to visualize what's going on. I'm going to tell you right now, for this class, you do not need to memorize those any of these rules. I will always give you the rules, or if you take an exam, you know, I might give you a sheet with the rule, but you'll never take a test where you don't have access to this. So you don't need to memorize it, but you do need to be able to apply it. That is, I will give you a Boolean function until you reduce it, and you're going to have to show all your steps and tell me which of these rules you're using on each one. So that's something you should practice. All right. Rule number 1, the associative. Oh, by the way, for almost all of these, there's two rules. There's the or version and the and version. They're the same thing. They're just inverse of each other. So the associative rules. P and Q and R is the same as Q and R and P. Right? And the same thing for or. It just means it doesn't really matter which order you do it in. Now you may wonder, then why did I tell you that you always want to put it in parentheses to show a certain order? That's to make it easier for me to read, right? But if all you have is ands or all you have is ors, it does not matter which order it happens in, right? That's what the associative rule means. So you can associate P with Q, or you can associate Q with R, or you can associate P with R by the same rule. You'll get the same result, all right? That's the associative rule. The distributed rule, I ran out of room. Shut up, this one's long. So the distributed rules say that P and, so in this case, we don't have ands and ands. We have ands and ors. And over here, we have ors and ands. And what this says is P and Q or R is the same as P and Q or P and R. And it makes sense, right? Let's look at it like this. Suppose P is 0. Then no matter what, the whole thing is going to be 0. So if P is 0, then anding it with this statement, doesn't matter what this statement is, the whole result will be 0. If P is 0, this will be 0. If P is 0, this will be 0. 0 or 0 is 0. If P is 1, then if either Q or R are 1, the output is going to be 1. So if Q is 1, then P and Q will be 1. Or if R is 1, P and R will be 1. And if as long as one of those is 1, then the whole output will be 1. So it works out being the same. I'm going to do an example with the next one, right? So P or Q and R is the same as P or Q and P or R. So let's look at this one here. P is 0. Both Q, in this case, Q and R both need to be 1 for this entire side to be 1. Agreed, right? Because we're anding these two together, and we know that the 0 is not going to contribute a 1 to each equation. On this side, because we are anding them together, because we're anding them together here, both Q and R need to be 1 for the entire output to be 1, because this side's 0. So in this case, for the output to be 1, both Q and R need to be 1, right? In all of the cases, the output's going to be 0 for both of them, so they're the same. But what if P equals 1? Then we have 1 or Q and R, which equals 1 or, I was just thinking about it, Q and 1 or R. In this case, what's the output going to be? Think about it. In this case, no matter what, the output's going to be 1, right? Because it doesn't matter if Q and R are 0, because we're ORing it over here. And this one's going to be 1 because it's an OR with a 1. This one's going to be 1 because it's an OR with a 1. When we AND them together, we're going to be 1. Again, the output is the same. So that's the key thing. With the distributive rule, I can distribute my ANDs into an OR statement or my OR into an AND statement, right? Which is the same thing you did with algebra in the past, right? That's the distributive rule. Idempotent. All right, so I'm getting idempotent rules. Says that P and P is P, P or P is P. Right? 1 and 1 is 1, 0 and 0 is 0. 1 or 1 is 1, 0 or 0 is 0. That one's pretty self-explanatory. But these come up a lot, particularly when you're building circuits. You end up with, the same output going into a gate, and this is telling you that you can, we can get rid of this and or this or. They're totally unnecessary. We can throw them in the trash. That's what this rule tells you. And that's what we want to do with algebra, right? We want to manipulate these functions to get them as simple as possible. You were doing it in your high school algebra class just to kind of understand the process. We do it here. Really, this is a big part of circuit design, and we get into it in CS61. This is how we reduce circuits. The double negation. This is only a single rule because there's no and and or equivalent. Not P is P. Right? If P is 0 and I have not 0, then that becomes 1. Not 1 means it's 0, right? Which was the original P. If we have not 1, we get 0. We not that, we get 1, which was the original value. And again, this is the kind of thing when you're trying to reduce a circuit, you end up with two negatives along the chain. You can use these other rules to move them next to each other, and that's a double negation. You can throw it out. DeMorgans Law, they call it DeMorgans Rule. I don't know why they call it DeMorgans. Maybe because they wanted everything to be the same, but it's DeMorgans Law. I like the name DeMorgans Law. It reminds me of an 80s cop show. You broke DeMorgans Law. So DeMorgans Law is what we were talking about earlier. And it says that not P and Q is the same as not P or not Q, and vice versa, right? If they're connected by an or, we can move the negation into the parentheses and actually get rid of the parentheses if we flip the sign. It's exactly the same as algebra, right? Remember when you would move the outside value, the negation in, and you just had to flip it, from times to divide, or it's the exact same thing. This one is harder to spot. It's harder to spot this situation, but it's very useful. Commutative rules, right? This is again just another way of saying order doesn't matter. Q and P is the same as P and Q. Q or P is the same as P or Q. And again, that rule allows us to move things around and put things next to each other that might, allow us to negate things or, get a double negative. The absorption rules, right? It says that P or P and Q is P. P and P or Q is P. Let's think about this. Suppose P is 0, right? 0, if this is 0, then that means, or 0 has no effect, right? We can ignore it. We only need to look at this one. 0 and Q is going to be 0, which means the output is 0, which was P, right? If this is 1, it doesn't matter what this is because this is an OR. So if P is 1, then the whole output was going to be 1, which is P, right? By the same token, I want you to do the absorption rule on the other side. Just take a minute, pause this, and do that absorption rule. You're going to come up with the same results. And again, this is reducing. We've reduced a couple of variables and two Boolean operators, right? So if this is a circuit, we've reduced a lot of the transistors. Our bound rules, right? So this is when we're dealing with constants. P and 0 is 0, right? No matter what. But P and 1 isn't always 1. It depends what P is. So P and 1 is P. P or 1 is always 1. Doesn't matter if P is 1 or 0 because it's an or, it's always going to be 1. But P or 0, if P is 1, the output will be 1. If P is 0, the output will be 0. So P or 0 is P. And again, we've reduced a gate here. We've simplified our circuit. And finally, we have our negation rules. The negation rules say that P and not P must be 0, right? If P is 0, then not P is good, then obviously it's going to be 0. If P is 1, then not P has to be 0, so the whole output must be 0. And by the other token, P or not P has to be 1, right? So if we're in this case, we can reduce these to a constant. If we can ever get P next to not P, we can reduce it to 0 or 1, which makes everything a lot simpler. So those are your rules. You have the list in your book. My advice would be cut it out, print it out, keep it handy. It's going to come up over and over again as we go through this unit. Okay?